Hey, good morning, everybody. Thank you guys for joining us. Really appreciate it. Also, really excited to have with us today Mark Lancaster of Baker Hughes. He's a senior sales manager of their turbo machinery process solutions. You're out in Midland, aren't you, Mark?
Yes, sir.
All right. Well, thank
Great
you for
West
joining.
Texas.
There you go. I hope everything's going well out there. Um, Wanted to first let everyone know I have everyone on mute. Pretty standard protocol for these virtual lunch and learns. Try and keep your microphones on mute as much as you can. Go ahead and use the Zoom chat to ask any questions that you might have, and I'll interrupt Mark and ask the question for you. We do that just for dogs and kids and various interruptions while we're all at home. So appreciate your consideration on that. And with that, I'm going to go ahead and turn it over to Mark, and we're all really eager to hear about what you have today. Thanks.
Oh, thanks, man. My name is Mark Lancaster. I'm with Baker Hughes. I'm in the turbo process machinery division. Work out here in West Texas in the vast Permian Basin oil field. Um, I came across or was, got involved in this technology. I had a facilities engineer who was in the process of designing what future facility pads would look like in the oil field. And he had asked me the simple question about, was there a way to create power with hydraulic flow? And I, being relatively new at Baker Hughes, did not know, made a one phone call and found out that yes, Baker Hughes has this really pretty cool product that we've been selling for many, many years and has had tremendous success to be able to convert fluid flow, and also gas flow in a pipeline or in a power plant, in a refinery, uh, to electricity, anywhere from 1 to 10, 15 megawatts of power can easily be pulled off of an existing flow. We're going to go through a basic presentation, and everyone should be able to see my screen now. And I just have to figure out the right button to push. Let's see. That's not working. Well, I thought I knew how I was going to do this. I took my other monitor off. Okay, so we're going to go back to this. So this is our standard PowerPoint for hydraulic power recovery turbines. And it's developed by our Nuovo Pignone facility people in Bari, Italy. But basically what a pump as a turbine is, it just allows us to be able to derive electric power from off of an existing hydraulic energy, hydraulic fluid flow. They have been in business for quite some time. It originally came from General Electric. When we split from General Electric in September, this technology became part of our process. And so there's multiple different solutions or adaptations, but basically an HPRT simply is a pump in reverse. Normally a pump has a suction and a discharge. Well, if you reverse the fluid flow in a pump and you force fluid through the discharge, you wind up spinning the impellers in reverse and causes you to be able to hook that to a drive, hook that to a generator so you can actually create power. And these are multiple different configurations. They're very easy to install and put in inline and existing flow systems. One of the first applications that I got involved with is that out here in Texas, had a company that had installed a pipeline from Lubbock, Texas, down to Jowett, New Mexico, bringing effluent water from Lubbock that they were buying from Lubbock, Texas, to agriculture oil companies down in Jowett. The nature of the pipeline was that as soon as it crossed the Texaco, New Mexico, everything was downhill. So all of this fluid would rush down the pipeline and build pressure in the pipeline. And typically they would go and install some type of pressure relief valve so that they wouldn't overpressure the pipeline. And by doing that, overpressurization, they might be running at 700 psi on the pipeline, and their preferences would be down to 450 or 500. We'll be able to install multiple units on that pipeline and get their pressure down to where they want to operate, and at the same time create almost 10 megawatts of power. This 10 megawatts of power, this group, what they're going to do is sell it back into the grid. So they'll wind up increasing their profits by about $180,000 a month. And that's not bad, and the cost of these pumps is fairly reasonable for like a megawatt of power. You can derive a megawatt of power for about $400,000 or $500,000 for a pump. There's different parts or classifications we look at, and we'll sort of talk about those later. In our references, we have over 100 of these installed around the world. In the United States, we have not ever used the technology that much, because for the most part, in the United States, people always consider, well, I have a grid, I have electricity right there. I don't need to conserve or do anything with getting more power. But as the oil field changes, the world changes, we see that if you have the ability to become more efficient by deriving power from where it's already there, basic example is solar power. You already have the sun. Well, why not monetize that and turn that into electricity? So here, you already have fluid flow. Why not monetize that and turn it into electricity? It's the same theory, same process. Here we've got 80 pups that we've done in the past 5 years. It continues to grow. It's really a big product that we do overseas, mainly because they have a lot of places where they have pipelines and they don't have access to power because they don't have a grid. So we can put in a pump, put in an HPRT, and provide them power. The applications of this transition, which I find are really interesting, anywhere where there's fluid flow, and one of the places in my past, in a reverse osmosis system, because in a reverse osmosis plant, you push in fluid at 1,500 pounds of pressure to push it through membranes that allow you to be able to have a clean water flow, and then you reject water. Well, that reject water typically comes out of the membranes at 800 or 900 pounds of pressure and flows into a reservoir or a lagoon or somewhere so they can be disposed of. But by installing one of these devices on that reject line, we can capture that pressure, turn it into electricity, and now reduce the operating costs of the RO system. Mining, we have an application in Michigan where they have, in dewatering their old abandoned wells or old abandoned mines, this type of technology can provide them the consistent amount of power they would need where they just don't normally have that. And then you can see some of the other examples. And I can make this presentation available to anybody that would like it. More often than not, you see this in depressurizing a pipeline, or really great example that I've come up with is that we have a oil refinery here in West Texas, and for decades they ran all of the equipment inside of the refinery on air pressure. So that way they eliminated the electrical spark of any electrical equipment. So what they did was they were using a diesel air compressor, rather large diesel air compressor. And this type of equipment will allow them to be able to use the fluid flow of all the fluid going through the refinery and gather electricity in places where they could switch over to electrical compressors, and thereby not only save themselves on the electric bill, but also save on having to pay for diesel and the emissions that come along with that. This is the typical system. We offer a number of these different methods depending upon whether it's just fluid or it's oil, depending upon the salinity of the water, if that's fluid, or if it's gas. We can do turbo expanders where we can expand the gas and create electricity. This gives you a size of our power ranges. And I think that's one of the things that you look at when you're talking about Baker Hughes. We can provide up to 10,000 pounds of pressure and up to 50,000 gallons of flow an hour. So these devices are meant for heavy duty, high flow, high pressure, and even we can get into low flow. It's always going to be a matter of two things. What's the amount of flow, and what's the differential pressure? How much pressure are we taking off the pipeline? This performance range, this is a multi-stage pump. It's a little bit more intricate. And that's pretty much the end of my presentation. But I have found that many applications in the oil and gas and agricultural area, we have groups in Wyoming that are looking at farmers needing electricity. They have all of these pipelines running across their property, and now they could gather and use that fluid flow to generate electricity to run some of their irrigation systems. So it's really been quite interesting to see how you can create power from a source of energy that most people didn't really think of.
Hey, Mark, we've had a couple questions come in. Yeah, I was going to say, first off, you're still sharing your screen there.
Okay.
But have you or Baker Hughes utilized any of these in offshore oil and gas applications?
It's a good question. I don't know whether we really have or not on the reference. I'm sure we probably have. Baker Hughes is pretty big in offshore, but I can definitely find out and get a reference on that.
Excellent. Another question that I had actually, are these more built for, I'm picturing like continuous runtime, like, the dams and reservoirs that you see these, turbine pumps creating power. Are they made for continuous runtime, or is there an application where they can start and stop if you're connecting it to a pumping system?
Yeah, I mean, it doesn't really matter from the way I understand it that, like it's just a pump and it's just spinning, when you have fluid flow. If you don't have any fluid flow, you can pull the clutch off and disengage the system. It's just spinning a generator. It's not really, it can be turned down. It can run at high level flow. It's not really going to be a matter as like you would sort of think. Doesn't affecting, like in your car, if you're going 100 miles an hour or going 10 miles an hour, car still works, just, you're a little safer at 10 miles an hour.
Right.
But
And
it's not, it's a pretty simple system as far as how it works.
sure, sure. What, in your experience, are people doing if there's excess power? A lot of these places, have small power lines or very remote where they don't really connect anything, and they don't really need to power all that much on a well pad or on a different site. What do you do with the excess power?
Well, you could store it. You can obviously drive it into a battery if you wanted to, but that is one of the other considerations. You're like, if we want to be able to place these in a location where the customer has access to use that power. No sense in creating the power if you don't have a true use for it.
Right.
But that's I think I mentioned two questions. Whether you have flow and differential pressure. Third question really comes out to what are you going to use it for? And more often than not, the question is, I'm going to drive other equipment or use it for other equipment that's out there. Rarely do people want to sell it back to the grid because it's more valuable for them to use it, than to go ahead and sell it to the grid. But that's an option too.
I was looking at your slides quickly there, and for everyone, we'll repost the video so you can go back and revisit what Mark talked about. But as far as rules of thumb for size range, can you go over that one more time? I think I like to leave people with, hey, we have 5 GPM or 500 GPM. What size are they looking for to, you know, at this type of application?
I was working on a project the other day, and they had 600,000 barrels of flow a day. And for that amount of flow, we were going to save them over $1 million a year in electricity when you figured their electric cost was about 4 cents a kilowatt. So that's a relatively large size system. On a smaller system we did that had 30,000 barrels a day of flow, and it was making them about $50,000 a year in electricity. So for typically the return on investment, which is always a big deal for people, is anywhere from 10 months to 2 or 3 years, depending on how you stretch it out.
Right.
And that's where not only are you able to get that electricity and use it differently, but the ability to say, and which is discernible, that your carbon footprint is going smaller. Because if you're able to create 2 megawatts of power in a place off of a pipeline that you needed, that means that you didn't have to buy 2 megawatts of power from the grid, and thereby reduce carbon footprint at that point in time too.
Yeah. So having a use for it is sort of turns into a big question, right?
Yeah, because I guess you could hook it up to your Tesla if you wanted to.
And then fluid-wise, you mentioned, there was some talk of gases in there. There's talk of water. Um, can you be pumping any type of fluid and make these things work?
Yeah, it seems like you can. I mean, I don't have all of the experience or knowledge. We have a lot of other guys who are pretty smart on that. But the basic definition is wherever you have fluid flow, or gas flow, because gas flows, through a pipeline, and we have methods to compress, and these recovery turbines are basically the opposite of a compressor. Where instead of compressing the gas, you're allowing it to expand out.
Perfect. Well, does anyone in our attendance have any other questions? We'll give it a minute to see. We got another question in here. So how is the discharge product handled? What is it? Go back into the line?
Yeah,
stored?
I mean, typically these are installed in line. So, you have a pipeline and you set one of these in the line so that as the fluid's flowing through there, it just turns the turbine that's inside of it, and it just goes from A to B, and it continues to go out. So there's really no discharge. The amount of maintenance on it's relatively low. In the gas turbine world, uh, normally we have people that are operating those devices because they're pretty large on a daily basis. But this is, just like a pump that sits there. It just sits there and run and generate power. So there's not a whole lot of other issues that go along with it. And they have a relatively long lifespan of 5 to 15 years, depending upon their use, the salinity, water, and other factors that are operating the pump.
Um, Interesting. Yeah. Um, any other questions? I think that's about it. Mark.
One of the interesting things that I hope that if everybody gets a chance to look at the video, this used to be a GE product. On the video, they show how in a plant where you have a 90-degree turn on piping, that these will often be set inside of that 90-degree turn, so that because that's where you're going to have a pressure buildup, and these turbines can be gathering that pressure and keeping the flow. And from a safety standpoint, by not over pressurizing a line, you're going to make that line safer. I greatly appreciate the opportunity, and if anybody wants to reach out, I'm on LinkedIn.
Yeah, everyone definitely reach out to Mark. He is on LinkedIn. You've probably seen his posts. They're always very informative. Also, I've been posting these on gatheringsystem.com, right? So just sort of a midstream focus, these lunch and learn type presentations. I've been trying to put them on there for everyone to go back and view. And Mark, appreciate it. Baker Hughes, I know this was a sort of a new thing during this lock-in, and really appreciate you and your team for allowing us to present with you today. So thanks everybody, and hopefully we'll see you next week. Have a
All
good,
right. Thanks,
good
Adam.
bye-bye.
Thank you, Mark.